Okay, so the distribution of x here is binomial, so we could, if we wanted to mathematically look at that formula, the probability that capital X would be equal to any little x value, it would be the number of trials, in this case 20, choose little x, times pi, which is 0.05, raised to the little x power, times 1 minus 0.05 raised to the 20 minus little x power. Okay? Now, if you were to evaluate this formula for all the values of x, that is, x could be 0, 1, 2, all the way up to 20, if you were to evaluate that, you would get a table like this over here. You would get this probability distribution here. I actually did this in Excel. Fairly straightforward to do in Excel, but I made this table and this chart in Excel. So here is the table with the associated probabilities, and here's the picture of that table. Okay, so make note of both of those. When you look at it, look at the picture in particular, that the bulk of the probability content is at the lower end of the possible values for x. And this makes sense because the probability of success here is so small. Alright. So, moving along here, if we want to do some computations, what is the probability that none of the 20 vaccinations fail? So again, out of the 20 people, what is the chance that none of the vaccines fail, or that x is 0? So that would be, well, what could we do? We could get it, yes, directly from this table here, 0.358, or we could use the formula, and I'll do it one time. 20 choose 0 times 0.05 raised to the 0 power times 1 minus 0.05 raised to the 20th minus 0 power. If you look at 20 choose 0, that's 20 factorial over 20 minus 0 factorial, which is 20 factorial, times 0 factorial. By convention, 0 factorial is 1, so my coefficient out in front here is 1 times 0.05 raised to the 0 power. Let me back up here. That's just 1, isn't it? Then times 0.95 raised to the 20th power. So if you punch that into your calculator, 0.95 raised to the 20th power, you should get 0.3585 is what I get on my calculator, and that's what Excel is giving us up here. Okay, so the chance that none of the vaccines fail, that they're all successful, is roughly 36%. All right. What is the probability that one of the 20 vaccines or vaccinations fail? All right, that would be the probability that x equals 1. Okay, again, if we wanted to use the binomial PMF formula like we did right here, we could do that, but I'm just going to appeal to the table that's got that probability. Here's that value here, 0.377. All right, so let me make sure 377 will go out to the third digit there. Okay, so the chance that one, now this is actually, to be more precise, this is a chance that exactly one of the 20 vaccinations fail. Another question that someone might have is, what is the chance that at least one of the 20 vaccinations fail? At least is what? It's 1 or more. So what is the probability that x is bigger than or equal to 1? Okay, how could we do this? Well, what is that? that would be the probability that X is 1 or 2 or 3 or 4, which would really be this. Now I could take the table here and I could add those 20 probabilities up. So here I could take this table and add all these up. By the way, these values are in scientific notation very small, basically 0 probabilities for those larger values of X. Okay, I could do that, or there's a quicker way. I could work through the complement rule. The complement rule would say, hey, do you remember the complement rule? The probability of A plus the probability of A complement is 1. In this case, this is like the A, and then the complement of that would be, let's see, if X is bigger than or equal to 1, what's the complement of it? Well, that it's strictly less than 1, right? Or for us, that would be that it's equal to 0, because X is just an integer, 0, 1, 2, 3, up to 20. So if I use the complement rule, I just look up here for that one probability, the probability that X equals 0. We computed that. It's also in the table here, 0.3585, 0.3585. Subtract that from 1 and you get 0.6415. Okay, so the chance that at least one of the vaccines fails is pretty significant, 64%. Notice that's different than the chance that exactly one fails. Now, number 4 here, what is the chance that at most one of the vaccines fail? All right, so make sure we're comfortable with the language here. At most 1, that would be the probability that X is less than or equal to 1, or the probability that X equals 0 plus the probability X equals 1. Okay, so I can add those two probabilities together. That would be 0.3585 and 377. Let's see, what was that fourth digit? 4. Alright, so adding these up here, let's see, 3585 plus 3774 is 0.7359. Okay, so the chance that at most one is almost 74% chance there. All right, last statement here. This is actually number 5. What is the mean number of vaccine failures out of the 20? So the mean here, in this case, the mean of X is, you recall the formula is n times pi. So that's going to be, n is 20, pi is 0.05, and so 20 times 0.05 is 1. Alright, so what that tells me, what does that mean? How do we interpret that sort of number? Okay, well, again, this mean, I've talked about it being the long run average, that out of 20, out of groups of 20, we would see the average number that for the vaccine that fails, that average number in the long run would approach 1. That's how we think of that long run average, that binomial average idea. Okay, so this wraps up the binomial distribution, which again is used to model the number of successes out of a binomial experiment. You can see here it has an example or an application in vaccine failures, and it's got applications all over the place. Wherever there's a Bernoulli trial, we can get this sort of distribution. And there's Bernoulli trials all over. So I hope this has been helpful, and this wraps up the binomial distribution